Hello, I am Petros Anastasiadis and I will present CoCoPeLia, a framework featuring communication computation overlap prediction for efficient linear algebra on GPUs. Linear algebra is extensively used in scientific codes in fields like machine learning, simulation, visualization, and many more. This led to the definition of the BLAS data, and since BLAS are suitable for GPU offloading, to the creation of optimized GPU BLAS libraries. These libraries usually offer end-to-end GPU offload in order to be used directly by domain scientists without code modifications. Therefore, since they are responsible for data transfer in the backend, they can utilize three-way concurrency overlap, a feature supported by modern GPUs which allows simultaneously GPU computations, host-to-device, and device-to-host transfers. To achieve this, GPU BLAS libraries split the initial problem to tiles to achieve overlap. The figure on the left shows the performance of 4 different dgemm problems in respect to the tiling size they use for overlap. Tiling size impacts performance considerably, and tiling size selection is a complex optimization problem which depends on routine, system, data, and problem-specific characteristics. Current approaches by GPU libraries are either including the tile size as an extra parameter, which is not ideal because the user is not aware of the performance trade-offs and the resulting code performance is system-bound, or predefining the tile size to a static value, which offers average performance and still requires empirical and benchmarks to find a good static value. For example, for a static tile size of 4096, there is a 15% and a 24% potential performance not utilized for 2 of the problems in the figure. Our proposed approach is a framework which couples performance modeling, automatic runtime tiling size selection, an optimized backend, and the unmodified BLAS API to the user called CoCoPeLia. Our presentation outline is the following. First, we go into more detail on three-way communication-computation overlap modeling. Then we describe the proposed end-to-end CoCoPeLia framework and its components. And finally, we evaluate our approach. Starting with three-way overlap modeling, we first explore previous work. There are a lot of models for GPU kernel computation, especially for BLAS, but these are not applicable to our case because they do not include transfer time. The work regarding specifically three-way overlap modeling is much more limited. First, we have Gomez et al. And later Verhoeven et al., which provide a three-way communication computation overlap model for CUDA streams. In their approach, they generalize the problem in order to be applicable in many overlap problems, which, as we will showcase later, results in limited accuracy in BLAS. Then we have the work of Liu et al., who, in order to simplify the problem, make many assumptions which do not hold for most BLAS routines. We therefore need to introduce our own three-way overlap models. We start from the common example of daxpy, a common BLAS1 routine. daxpy uses 2 data vectors, which we parameterize with OPD, and each is split into k equal tiles, creating k independent sum problems. Then, the host-to-device computation and device-to-host transfers for its subproblem are scheduled to the GPU and can overlap with distinct parts from other subproblems. The execution time of a single tile for each of these parts are modeled with 3 different functions, which are estimated semi-empirically, as we will show later. Using this, we construct our baseline model for total offload time. The model represents that the total offload time of a kernel is the max of the computation, host-to-device and device-to-host transfers for the intermediate part that can be overlapped, plus the first host-to-device transfer and the last computation and device-to-host transfers that cannot be overlapped. But the baseline model can overestimate transfers since first, it assumes all data are initial input and output, which is our example, does not stand for the X vector. And second, it assumes that all data is initially on the CPU. To fix this, we add data requirements and location to the equation for its vector or matrix, which can be easily extracted from a routine in runtime. By applying this to the baseline model, we create a data location aware model. Then the next problem we face is bidirectional slowdown. Three-way overlap assumes host-to-device and device-to-host transfers can be fully overlapped, but in real systems, the channels they use share resources like the PCIe or NVLink, depending on the system. This results in a slowdown where they are used simultaneously, imposed to both transfers, which we model with an extra slowdown coefficient, also estimated semi-empirically. But This is not sufficient because the two transfers are not always equal, so bidirectional overlap only occurs for a portion of the longer transfer, as we can see in the figure. The rest continues without a slowdown. We generalize to any two transfer overlapping with this equation, and we apply it to the data loop model, ending up with a bidirectional aware three-way overlap model. Finally, the last problem we face is that level 2 and 3 BLAS reuse data. For example, for a case of gem offload, we see here that the problem is initially transfer bound, then transfer time for each sub-kernel decreases since it reuses data, and finally it becomes computation bound for the last sub-kernels. Since all previous models are not aware of reuse, they always overestimate transfer in such scenarios. To solve this, we add a k-in parameter, which calculates the number of sub-problems requiring transfers. Assuming each of these k1 subproblems requires one transfer, which is a close approximation when we have many tiles, we arrive to a data reuse-aware model for three-way overlap. The model differentiates from previous ones in recognizing a potential area of k minus k that the problem becomes computation-bound due to reuse. Next, we continue to introduce the proposed framework. The CoCoPeLia end-to-end framework consists of three different distinct components. The deployment phase, which feeds the runtime with semi-empirical submodels, the tile selection runtime, which employs the described prediction models to provide near-optimal tiling sizes, and the library and tile scheduler, which implements an optimized subset of BLAS kernels. Finally, all these are coupled to an unmodified BLAS API to hide optimization details from the user. The first CoCoPeLia component is the deployment phase. It starts with running a set of offline lightweight micro-benchmarks for transfers and BLAS routines, which are configured and executed on a new system automatically. Then the results are used to initialize a semi-empirical model for transfer times using linear regression to obtain latency bandwidth models both for single and bidirectional transfers. In the case of GPU computation time, an analytical model would require more intensive benchmarks, and since we are only interested in square tiles for level 3 and one-dimensional tiles for level 1 and 2 BLAS, we use value lookup as a function of tile size. Finally, the results are stored in files in order to be used from the tile selection runtime. The second component is exactly the tile selection runtime, which loads the transfer and computation submodels and combines them with problem-specific parameters extracted from a BLAS call in runtime. Then, it uses the aforementioned prediction models to provide near-optimal tile selection by iterating over available lookup tiles and selecting the one which minimizes time. Finally, the third component is the library and tile scheduler, which initializes resources like buffers, streams, or library structs the first time it's called with certain parameters, since subsequent calls reuse these resources. Then it schedules subproblems with the t-best obtained from tile selection, respecting dependencies and utilizing data reuse when possible. Finally, it executes all transfers and computations of subproblems with wrapped optimized library calls utilizing CUDA and cuBLAS in our case. We continue to the evaluation of our approach. We use two validation sets, one for daxpy and one for sgemm and dgemm, and two testbeds with different computation transfer ratios to show the portability of our method in multiple scenarios. We evaluate our approach on three axes: the model error in three-way overlap time prediction, the tile selection ability of our models, and the end-to-end CoCoPeLia performance. First, we evaluate the error for cases without reuse. We compare Verhoeven's three-way stream overlap model, the CSO model as we call it, with our BTS bidirectional model. First, we explore the case of daxpy, which has no reuse. Most models have low, with BTS having slightly better median error, which becomes more evident on testbed 2, where the bidirectional slowdown is large. Then, we use cuBLAS dgemm, which has been proven not to utilize data reuse well. We see a major underprediction for both models, which is expected since cuBLAS has internal buffer initializations and other overheads not included in most models. But the BTS model still has much better medians and error distribution, especially in transfer-bound cases where the CSO model error increases considerably more. Then, we evaluate the error for cases without reuse, with reuse. We compare the CSO model, but now modified with added data location awareness for better reuse-related comparison with our data reuse DR model for the CoCoPeLia implementation of dgemm and sgemm with fully utilized reuse. The CSO model underpredicts times considerably, while the DR model has much better medians and error distribution. Again, the CSO model error increases in transfer-bound cases, while the DR model has similar performance. We therefore can conclude that the CoCoPeLia model successfully captures BLAS data distribution patterns. Then, we evaluate the tile size selection ability for our models by comparing the tile selection performance achieved by our various models and the CSO model for dgemm in testbed 2 versus a static tile size as a baseline, as we can see in the figure in the example. First, we see that there is considerable 13.5% speedup potential over the static tile with the optimal tile for all cases, which of course we found experimental. Then we see that the CSO model predicted tiles actually result in a nearly 10% slowdown. It is therefore completely inefficient for tile size selection in practice. On the other hand, our baseline provides a 7% speedup, capturing some of the potential performance but missing the maximum. Then the datalog model improved this to 10% with better prediction for cases with non-CPU data location, which, as you can see in the figure, are the 2/3 of the total cases. And the BTS model follows it, since the explored dgemm case has very low device-to-host transfers and therefore very limited bidirectional overlap. Finally, the DR model offers 12.4% speedup, which is very close to the optimal selection, and we can conclude that CoCoPeLia runtime provides near optimal tiling size selection. Last, we evaluate the end-to-end performance of CoCoPeLia versus two optimized end-to-end offload libraries: NVIDIA's cuBLAS using the optimized tile size for its problem, and BLASX using a predefined static tile size. The first case is a square problem with only the C matrix on the CPU, resulting in a load transfer scenario. CoCoPeLia shows similar performance with cuBLAS, resulting in an average speedup of 8%. On the other hand, for the full offload scenario, where all data is initially on the CPU, which is the second red case, we see that it has considerable average speedup of 17% over the best of the two other libraries. Finally, for a full offload case of a non-square problem, which results in a very transfer-heavy scenario, it shows a large average speedup of 26% among the best of the other two libraries, benefiting from the additional overlap potential that it can utilize. Then we conclude that CoCoPeLia actually outperformed competitors, and especially in transfer-heavy scenarios. Summarizing, three-way overlap is not well utilized in GPU BLAS, since tile size selection is a complex optimization problem. To this end, we propose CoCoPeLia, an end-to-end framework which provides BLAS applicable three-way overlap prediction models for offload time, offers automatic tiling size selection during runtime, and uses an optimized backend for tile scheduling and execution. We evaluate this framework, CoCoPeLia, for dgemm, sgemm, and daxpy in two testbeds, demonstrating much lower model error than previous models, near optimal runtime tile selection, and considerable end-to-end performance improvement. More specifically, CoCoPeLia achieves a 5 to 15% average speedup over optimized end-to-end GPU offload libraries, cuBLAS and BLASX in our case, and 16 to 33% when offloading all data from the CPU, which is the most commonly used scenario in such works. Finally, for future work, CoCoPeLia is easily extensible. New routines, models, micro benchmarks, or any combination of the above can be added without modifying all components, and the backend kernels can also be replaced with custom implementation or other libraries in order to improve performance. For more details on our work, we welcome you to read our ISPAS 2021 paper. Thank you for your time and stay healthy.